Welcome to our latest video on the topic of acids, bases and the pH scale. This video is suitable for GCSE students. By the end of this video lesson, you should be able to explain the meaning of the term acid. You should be able to list examples of acids, including their chemical formula, and be able to explain the difference between strong and weak acids, as well as dilute and concentrated acids. You should also be able to explain the meaning of the term base and alkali and the difference between strong and weak alkalis. And finally, you should be able to explain the role of indicators and understand that acidity and alkalinity are measured using the pH scale. In our daily lives, we come across many different substances that are acidic, from the acid in our stomachs to the citric acid in oranges and lemons, to the malic acid that's in our apples that we eat, to the acid in our batteries, to the vinegar which contains ethanoic acid which we place on our food for flavouring. These acidic substances are everywhere, and it's important that we are able at GCSE to define the meaning of the term acid. Now at GCSE we define the term acid as a substance that splits up into H+ ions when placed in water. Now a H+ ion is called a proton, and this is because hydrogen is the only element in the periodic table that you will come across that doesn't contain any neutrons. And each hydrogen atom contains one proton and one electron. And when a H+ ion forms, the electron is lost. And that's why a H+ ion is simply called a proton. Now, the acids that you should learn for GCSE are hydrochloric acid, which has the chemical formula HCl, sulfuric acid, which has the chemical formula H2SO4, nitric acid, which has the chemical formula HNO3, and ethanoic acid, which has the chemical formula CH3COOH. Now you'll notice that all these substances contain hydrogen, and acids all split up into H+ ions when in water. So the first thing we're going to look at in this video is the definition of a strong acid. Now a strong acid is a substance that totally splits up into H+ ions when placed in water. So if we look at the equation here, we have hydrochloric acid, HCl, and you can see that I've drawn a single arrow to show that it totally splits up into H+ ions and Cl- ions when in water. Now this is not reversible, and every molecule of hydrochloric acid here would split up into a H+ ion and a Cl- ion. And you'll notice I've also put AQ in brackets, which means aqueous, and that just reinforces to you that acids show their properties in water. They split up into H+ ions when you put them in water. Now the more H+ ions in solution, the more acidic a substance is. Now strong acids include hydrochloric acid, nitric acid and sulfuric acid. And if I had 1,000 molecules of HCl, I would have 1,000 H+ ions being formed, because every hydrochloric acid molecule splits up into H+ ions when you put it in water. Now a weak acid is a substance that only partially splits up into H+ ions when you put it in water. So I've drawn ethanoic acid here, CH3COOH, and the aqueous sign, AQ, denotes that this is placed in water, and it splits up into H+ ions and ethanoate ions, CH3COO-. And you'll notice that I put a reversible sign, because when ethanoic acid splits up into H+ ions and ethanoate ions, the ethanoate ions and the H+ ions can rejoin and form ethanoic acid. Now the fact that these H+ ions and these ethanoate ions can recombine and form ethanoic acid means that if we look at 1,000 ethanoic acid molecules, only about 4 would be split up into H+ ions at any one time. And that's because the others are just rejoining and forming ethanoic acid. So therefore, for every 1,000 ethanoic acid molecules, we only have about 4 H plus ions. So there's much less H plus ions being produced for a weak acid. And remember, the more H plus ions in solution, the more acidic a substance is. And weak acids have less H plus ions in solution because of the fact that the process of splitting up into H plus ions in the very first place is a reversible process. Now, most of you will be familiar with the term pH, which measures the acidity and alkalinity of a substance. And substances that have a pH of less than 7 are deemed acidic. Now, all the pH scale is measuring is the amount of H plus ions in solution. And the H in pH stands for hydrogen. It's a measure of how much H plus ions there are in solution. And the more H plus ions in solution, the lower pH, and the more acidic a substance is. So what will ultimately decide the pH of a solution and the acidity of an acid will be, first of all, how many acid molecules are present. So in other words, how concentrated is that acid solution? If it's got lots of acid molecules and not much water, we say it's a concentrated acid. And if it's got very few acid molecules and lots of water molecules, we say it's more dilute. Now, the concentration of an acid and the number of acid molecules obviously affects how much H plus there is in solution, as well as the chemical properties of that acid, whether it's a strong acid and totally splits up into H plus ions, or a weak acid and partially splits up into H plus ions. Now, the chemical opposite of an acid is called a base, and a base is any metal oxide or hydroxide. So if we're going to name a base, all we have to do is name a metal. So let's say copper, and if you add the word oxide or hydroxide after it, you have the base. So copper oxide is a base, copper hydroxide is a base, magnesium oxide is a base, magnesium hydroxide is a base. Now, there are around 90 metals in the periodic table, so if there are oxides and hydroxides of all those 90 metals, you can see there's 180 bases at least. And bases that dissolve in water have a different name. They're called alkalis. So an alkali is a soluble base. Now, most bases are insoluble. However, a few dissolve in water. For example, sodium hydroxide is a base that dissolves in water, and therefore it's called an alkali. Now, you'll notice that NaOH in this equation splits up into Na plus ions and OH minus ions. And the difference between an alkali and an acid is that the alkali will split up into OH minus ions when you put it in water, and the acid will split up into H plus ions. Now, when an acid and an alkali react together, it's the H plus ions from the acid that react with the OH minus ions of the alkali. A neutralization reaction takes place, and we produce water. Now, sodium hydroxide is classed as a strong alkali because it totally splits up into OH minus ions when you put it in water. Weak alkalis only partially split up into OH minus ions. Now, examples of alkalis include lithium hydroxide with a chemical formula LiOH, sodium hydroxide with a chemical formula NaOH, potassium hydroxide KOH, and ammonium hydroxide NH4OH. Now, you'll notice that the first 3 alkalis in this table are all group 1 metal compounds, and group 1 is called the alkali metals. And group 1 elements have this name because when you put lithium, sodium, potassium and other group 1 elements into water, they react violently and form metal hydroxides and hydrogen gas, and the metal hydroxides are alkalis. So group 1 metals are called alkali metals because when you put them in water, they form soluble bases called alkalis. So this work ties in with previous topics you've studied at GCSE. Now in this video we've talked about weak acids and strong acids, and we've also mentioned that you can have concentrated acids and dilute acids. So it's important to recap what we mean by dilute and concentrated. If you have a dilute acid, it means that you have lots of water molecules and a small number of acid molecules. And if you have a concentrated solution, you have a lot more acid molecules and fewer water molecules. So a concentrated solution has a greater amount of the solute rather than the solvent, and a dilute solution has a greater amount of solvent molecules compared to the solute. So it's worth mentioning this because obviously the pH of an acid depends on the concentration of that acid, how many acid molecules you have, as well as the chemical property of that acid. Is it a strong acid that totally splits up into H+ ions when you put it in water, or a weak acid that only partially splits up into H+ ions when you put it in water? Now indicators are chemicals that help scientists to distinguish between acids and alkalis. And during your time at school you would have come across lots of different types of indicators. For example, you may have come across making your own indicator in the form of red cabbage and using that to test for an acid. You may also have come across litmus, and litmus is an indicator that turns red in acid and blue in alkali. Now litmus is available as a liquid, like most indicators, and can be added to the solution, and it's also available as strips of paper, so you can add a drop of the solution to the paper. And if you wanted to test for an acid, you would use blue litmus, and if it turned red, that would prove that you had an acid. Now if you're testing for an alkaline solution, you would add red litmus, and if the red litmus paper turned blue, that would prove that you had an alkaline solution. Now if you have a neutral substance, if you add red litmus paper or blue litmus paper, you will see no colour change because a neutral solution will not turn red litmus blue and it won't turn blue litmus red. So you have to be aware of that as well. Now a drawback with using litmus is that litmus will tell you whether a solution is acidic or alkaline, but it won't tell you how acidic or alkaline a substance is. Now to do this we need to use an indicator called universal indicator. And universal indicator is a mixture of different indicators and has a whole range of colours that tell us how acidic or how alkaline a substance is. Now the colours you get with universal indicator tell us the pH of a substance. And as I've mentioned previously, the pH scale is used to measure acidity and alkalinity. Now the following slide shows the pH scale and the colours that are obtained with universal indicator. So acids are substances that have a pH of less than 7. Alkalis are substances that have a pH of more than 7. And if a substance has a pH of 7, the substance is classed as neutral. Now typical colours observed with universal indicator for strong acids are red and orange, and as universal indicator becomes more yellow with a substance, that is an indication that the acid is weaker. And if universal indicator goes green, that represents a neutral solution. And if we end up with dark green, blue and purple as a colour, that will indicate that the substance is alkaline. So substances that have a pH of less than 7 are acids, more than 7 alkalis, and a pH of 7, neutral. And you can see in this slide that acids include stomach acid, vinegar, lemons, battery acid, tomatoes, and neutral substances include water, and substances such as stomach tablets, indigestion tablets, ammonia solution, bleach, soap, cleaning products such as drain cleaner are alkaline in nature. So now let's test your understanding of what we've covered in this video with some practice questions. So here's our first practice question. So read through the question, pause the video, have a go at it, and then we'll go through the answers. So question 1 is asking you to name 3 other acids other than hydrochloric acid and write chemical formula for each of them. So you could write down sulfuric acid with a chemical formula H2SO4, nitric acid with a chemical formula HNO3, ethanoic acid with a chemical formula CH3COOH, and those would be 3 acids that we would expect you to know for the GCSE syllabus, and there's 1 mark for each of those. Now for question B, you're asked why sulfuric acid is classed as a strong acid. So this is a 1 mark question. So you need to say that sulfuric acid totally splits up into H+ ions when placed in water. Now to illustrate this, I've written the equation for sulfuric acid splitting up. So you can see that H2SO4 would split up into 2 H+ ions and a sulfate ion, which is SO4 2-. Now for question C, you're asked why potassium hydroxide is classed as a strong alkali, and this is 1 mark again. So this is because potassium hydroxide totally splits up into OH- ions when you put it in water. 1 mark for that. Now once again, I've illustrated this with an equation. KOH splits up into K+ and OH- ions. For part D, you're asked to give the term that is used to describe a base that dissolves in water. So a base is the opposite of an acid, and a base that dissolves in water is called an alkali, and there's 1 mark for that. So here's our second practice question for you to have a go at. Once again, read through the question, pause the video, have a go at it, and then we'll go through the answers. So now let's go through question 2. So question 2A is asking you to put a ring around the colour of universal indicator in a neutral solution. So the answer for this is green, 1 mark for that. Then it says which substance in the table is neutral? Well, it would be water, because water has a pH of 7, 1 mark for that. Then for part C, you have to name 1 substance that is an alkali. So you need any substance here that has a pH of more than 7. So you could go for oven cleaner. Now oven cleaner has a pH of 14. You could go for toothpaste, which has a pH of 8. Or you could go for window cleaner, which has a pH of 11. All of these are alkalis because they have a pH of more than 7. 1 mark for that. Then it says how many substances in the table are acidic? Well, there's 3. There's acid rain with a pH of 3. There's carbonic acid with a pH of 1. And there's vinegar with a pH of 4. So 1 mark if you said 3 substances. And then for part E, they're asking you to name the gas formed when a metal reacts with an acid. Now you've got to remember that acids contain hydrogen. So if you react a more reactive metal than hydrogen, so for example magnesium, you would kick out the hydrogen in an acid here. So the gas formed is hydrogen. 1 mark for that. So here's our last practice question, question 3. Now question 3 has 3 parts to it, A, B and C. Parts A and B are on this slide and part C is on the next slide. So read through the question, pause the video, have a go at parts A and B, and then we'll look at part C. And then once you've done A, B and C, we'll go through the answers. So here's part C. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers to parts A, B and C. So now let's go for the answers to question A and B. So A is asking you to complete the table by filling in the 2 empty boxes. So a substance that goes green with universal indicator and is neutral has a pH of 7, and a substance that goes blue with universal indicator and has a pH of 8 to 10 is a weak alkali. So there's 2 marks for that. And then for part B, you're asked to use the table to help you answer these questions. So this first part says Jody adds universal indicator washing up liquid, it turns blue. This shows washing up liquid has a pH of, so you use the table, so if it turns blue, it has a pH of 8 to 10. 1 mark for that. Now for part C, it says Jody adds universal indicator to lemon juice and it turns orange. Jody writes this conclusion. Now Jody's conclusion is that lemon juice is a strong acid with a pH of between 4 and 6. And the part 1 says, do Jody's results match her conclusion? Well, the answer is no, because turning universal indicator orange means it's a weak acid, not a strong acid. So if you said that, you get the 2nd mark. So there's 2 marks for part C. So that concludes this video lesson. So after watching this video, you should be able to explain the meaning of the term acid, be able to list examples of acids, including their chemical formula, and be able to explain the difference between strong and weak acids, as well as dilute and concentrated acids. You should also be able to explain the meaning of the terms base and alkali, and the difference between strong and weak alkalis. And finally, you should be able to explain the role of indicators and understand that acidity and alkalinity are measured using the pH scale. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.